Hello everyone! Welcome back to another video where we are going to be evaluating this cool little integral I found while paying attention in class. So without any further ado, let's get started, shall we? One way we can express this natural log term in the numerator is actually with Feynman's technique. So we can say that natural log to the n of x is just equal to the nth derivative, say with respect to t, of just, well, x to the t, evaluated at t equals 0. That way we eliminate any x terms that are left over, and the only thing we're left with is just the natural log to the n of x. So substituting this in and reversing the order of integral and derivative, we find that our integral is actually just going to be, I'm going to abbreviate our derivative as such right here, so d over dt, integral from 0 to infinity of x to the t, divided by x squared plus 1 dx. And now, this integral right here might look maybe a tiny bit familiar. If you're familiar with all the wacky identities for the beta function, the normal beta function, not the Dirichlet beta, which we will be dealing with later, this one resembles one of them quite well. And to attain that form, what we're going to do is let u equal x squared. So that means du over 2 times the square root of u is just going to be equal to dx. So our integral then is equal to, well, the derivative part is not going to change, integral from 0 to infinity, but our x's are, so the denominator is going to become u plus 1, then we have our du here, and let's not forget the half out front. But what is this x then? It's going to be x to, u to the t over 2, but then minus a 1/2. So it's really a u to the t minus 1 over 2. And now here is actually where we get to apply our beta function. So this right here, this integral right to here, is just beta. So I'll do a little arrow. This integral right here is just beta of t plus 1 over 2, and then comma 1 minus t plus 1 over 2. The reason we know this, using the notation from Wikipedia, is that we can say z1 minus 1 is equal to t minus 1 over 2. So everything that's in the numerator, exponent right there. And then z2 plus z1 must equal the exponent right here for all of these terms. But that right there, that looks like a 0. That's just a circle. There's an implied 1 here, right? So we know z1 plus z2 is just going to be equal to 1. So solving for both z1 and z2, we obtain the following for this right here. And the interesting thing about this is that normally whenever we do Feynman's technique for something involving the beta function, a lot of the times we end up with, derivatives obviously for the beta function, or gamma function, pardon me, but we usually end up with some gamma term in the denominator that makes it just kind of tricky. But in this case, we are saved by a couple of things, namely that z1 plus z2 is just equal to 1. So when we go to, convert this to the gamma function, our denominator is just going to be 1, because gamma of 1 is just 1, right? So we have gamma of t plus 1 over 2, and then just times gamma of 1 minus t plus 1 over 2. But here's the interesting part. This right here is just, kind of again, another identity, namely Euler's reflection identity or formula. I forget exactly what it's called. But it's the one where, it's the one where, in general, gamma of 1 minus x times gamma of x is just equal to pi over sine of pi x. So using this right here, we can convert everything with a gamma in it to the following. We can say this right here now is equal to pi over the sine of pi, and then times t plus 1 over 2. Now that we've evaluated the integral part, we can bring down all of our derivative bits and also the 1/2. So what this is in total then is dt, the nth derivative, or 1/2 times the derivative with respect to t, of pi over sine of pi times t plus 1 over 2. And now, and I should specify this is being evaluated at t equals 0. Now it's just a question of, well, what on earth is the nth derivative of this random cosecant? And the answer to that is actually just going to be answered by a series. So one way we can express sine, similar to actually the previous video, is the following. So 1 over sine of some x, we can express, I should do this in a different color. Ooh, green, I say. So we can express 1 over sine of x as just 2i over, well, e to the xi minus e to the minus xi, but multiplying the numerator and denominator by e to the minus xi, we obtain 1 minus e to the minus 2xi times e to the minus xi. You can see where you distribute the numerator right there, you get what you typically see for sine. And then we can express this right here as a series subsequently. So we can just say this is now the sum from k equals 0 to infinity of, well, e to the minus 2xik minus xi, just combining all of our e terms, but we can factor out our a minus xi here, which leaves us with, if I can erase, 2k plus 1 times xi. So now it's just a question of, well, what's our x? And that right there is just going to be this whole term right here. So pi times t plus 1 over 2. So let's go ahead and sub that in, shall we? So just evaluating this bit right here, because that's the bit we're concerned with, we now have the sum from k equals 0 to infinity of e to the minus 2k plus 1 times pi I over 2, and then times t plus 1. And then now we just have to throw in the 1/2 and take the derivative with respect to t. And it doesn't seem all too bad now, because we're just differentiating an exponential with respect to something in the exponential. So we know how to do that, right? And all we have to do then is just evaluate this at t equals 0. So let's get started. Scrolling on down a little bit more. Ooh, that's... Oh, I know texting came out. Oh gosh. Anyway, I might cut that part out, or not. So evaluating this nth derivative, we know that, just in general, that the nth derivative of some e to the t, or e to the at, is just going to be equal... That looks like a 9. Goodness gracious me. That the nth derivative with respect to t of e to the at is just going to be a to the n times e to the at. This just comes really from the chain rule. So under that same logic, we have, well, 2k plus minus 2k plus 1 times pi I over 2. That right there is our a, which is a mouthful, but it does get us somewhere rather interesting. So we still have our sum. So sum from k equals 0 to infinity, and let's not forget the 1/2 up front, because we don't want to do that. And we have minus 2k plus 1 times pi I over 2, all to the n. But then we have our e to the minus 2k plus 1 times pi I over 2, and then times t plus 1. But remember, we are evaluating this at t equals 0, so we can really just drop this whole term, or the t plus 1 term right here, because, you know, plug in 0, you just get 1, so multiplication by 1 is implied. And we can evaluate just this straight off the bat, this e term right here. And that right there is going to, this right here is going to equal, let's think about this, pulling out the good old unit circle. This in the previous video as well. Funny how these things overlap, actually. But plug in 0, right? We get e to the minus pi over 2, so we're going to end up down here. Plug in, say, k equals 2, we end up with minus 3 pi I over 2, which is the same thing as pi I over 2. And then if you keep plugging in values, you'll realize that we're just going this way around the circle. So one way we can actually express this term for integer k is just negative, or I times negative 1 to the k minus 1. So subbing all that in, we have a 1/2 times the sum from k equals 0 to infinity of negative, I changed my mind. I'm going to pull out the pi I over 2 to the n real fast out of the sum, just to make it clear what we're summing over. So there's a minus there. I'll write the minus as its own term, actually. I don't want to get that confused. And then we have our sum from k equals 0 to infinity of, well, I times negative 1 to the k minus 1, and then times 2k plus 1 to the n. And before I forget, we do have, from our sign, an extra factor of 2i here. I do apologize. I should have written that in earlier, but there is a 2i that is all being multiplied throughout here. So let me just add in this 2i real fast. So that way these terms will actually cancel. And subsequently that the i's right here will make a negative 1, meaning that we just cross off this negative 1 in the process as well. So rewriting everything once more, we have pi I over 2 to the n times negative 1 to the n of our sum from k equals 0 to infinity of negative 1 to the k, and then I'm going to rewrite this slightly differently, and then 2k plus 1 to the n, pardon me, minus n. And now here's really the interesting part. What happens when k is even? Well, you'll see that we very clearly get just some sort of real number because we're squaring I. So that's going to become a negative 1 to some power. But the moment we have something that is odd, right? Say 2k, or say 2k plus 1, just in general. What we have then is just an extra I term. And we know our integral is going to be, well, completely real because it has no imaginary part. So one thing that we can actually conclude about this is, well, the following, is that n must be even. And say you still aren't fully convinced by this. Let's write down our original integral to begin with. So integral from 0 to infinity of natural log to the n of x over x squared plus 1 dx. And now let's consider the transformation at u equals 1 over x, right? So if we let's just let n be odd real fast, right? So that means we can express our integral as ln of, well, I'll just use m. So 2m plus 1 times, well, or not times, of x, but what is x? Just 1 over u, right? So we can say this is 1 over u, but one way we can express this 1 over u term by properties of, well, logarithms is just you move the negative 1 that's in that exponent outside of it, right? But because this is a log raised to some power, what we have is that negative 1 being raised to 2m plus 1, but the 2m term doesn't really matter because we're squaring the negative 1 anyway. So we just get an extra negative sign here, right? And then we have the integral from 0 to infinity. Our bounds aren't going to change. And whenever we find our du, so du equals 1 over x squared, or minus 1 over x squared dx, that minus sign will just be used to change the bounds again. So the minus sign of the bounds does cancel out. And what this leaves us with is a 1 over u squared plus 1. But then we have to, can't forget about this part right here. So we have minus x squared, but x squared is just 1 over u squared. Du equals dx. And again, the minus sign is just being used to change the bounds, so we just have to distribute this 1 over u squared to everything, which leaves us with the following, just u squared right here. And what you'll see is, if we actually replace this right here, so 2m plus 1, is that we can both agree that these both are our integrals right here. Like all we did was a transformation. And if I equals negative I, well, the only number that does that is, well, 0. So I must equal 0. So in either case, the point is here is that n must be even because, well, whenever n is odd, we either get an imaginary part right here, which just completely doesn't make sense. And also just a side note that the Dirichlet beta function is actually just 0 for every negative odd integer, which is another way you could have done this. But you could also say, we get an imaginary part, which doesn't make sense. And also, just by this transformation, the integral is just 0. So at any rate, n must be even. With that in mind, we can now express n as just some 2m, for example. So what does our entire sum become? Well, drawing a big ol' arrow down here, we find that our sum becomes, well, pi I over 2 to the 2m. And that -1 term is actually just going to go away completely. And we have our sum from k equals 0 to infinity of -1 to the k over 2k plus 1 to the minus 2m. And I am realizing now, I do sincerely apologize, that there is an extra factor of pi that came from our identity right here, so I do apologize. This factor of pi right here, I can use a little highlighter. Oh, that just makes it green? Yo, okay, that's actually so cool. Okay, anyway, this extra factor of pi right here, I did actually forget to, that looks really ugly now with the colors, but anyway, this factor of pi I did actually forget to include. I do sincerely apologize for that. So there's an extra factor of pi out here. I am sorry. Apologies if that didn't make sense. But now we're in a very good position to just evaluate this integral right here, or integral expression. So what we have, I'll start with this part right here, is a pi to the 2m plus 1, and then times a 2 to the minus 2m. But then what exactly is this right here? Well, that sum is just defined to be the Dirichlet beta function of, well, the exponent right here, which happens to be beta of minus 2m. And that right there is just our answer for this integral. So again, n must be even, because if it's not, the whole integral just goes to 0. So we can actually express this in a different way, because we have everything with 2m's here. We can say that for even n, what we have is just pi to the n plus 1 times 2 to the minus n, and then times beta of minus n. And this actually would still work in general, because the Dirichlet beta function of just some negative integer is just negative odd integer. It's just 0. But at any rate, that's our answer. Thank you so much for watching, and I will see you in the next one.